Roots to grammatical complexity. Here's a simple story. See if you can understand it. Girl fruit pick, turn mammoth see. Girl run tree, reach, climb, mammoth tree shake. Girl yell yell, father run, spear throw. Mammoth yell, fall. Father stone take meat, cut, girl give. Girl eat, finish, sleep. This story, modified from Guy Deutscher's The Unfolding of Language, contains 23 different words arranged to violate English grammatical rules. Yet you probably more or less understood the story. Deutscher used some basic principles that are probably rooted in our ape cognition to construct the story in an understandable way without relying on English grammar. First, he used proximity. Words for things that are closer in space are closer in speech. They go together. This doesn't have to be the case in many languages, but it's our initial inference. Second, he used temporal sequencing. The events in the story follow the events in reality. Third, he relied on non-linguistic causal structures. Research with speakers from diverse languages suggests that actors, subjects, are first in thought. After actors, humans are next inclined to think of objects, patients, and finally, actions, verbs. You can understand girl fruit pick more easily than fruit girl pick or pick fruit girl, even though none are the subject-verb-object that English normally requires. So, you can achieve some degree of communication, even telling a story, with just some shared vocabulary. In fact, not only do you not need grammar, but you can also do it even when the organization of the words violates the rules of your own language's grammar. This means that cultural evolution could gradually increase the complexity of a simple proto-language, involving, say, 23 words, by incrementally adding grammatical rules and tools to its stockpile of words. We now know something of how this happens. Detailed historical and comparative studies show where specific grammatical elements come from and how they usually evolve. They typically come from first hijacking concrete words, then gradually bleaching them of their original meaning, and often then honing them down to size, presumably to increase communicative efficiency. This process is called grammaticalization. Here is a taste of grammaticalization. 1. Adjectives. Nouns and verbs, which are built on an ancient cognitive distinction between things and actions found in non-human primates and presumably in our ancient pre-cultural ancestors, get deployed to build adjectives and adverbs. For example, a word for a rock-solid thing like concrete, cement, water, and gravel, can evolve to also operate as an adjective, meaning not abstract, as in, give me a concrete example. Someday, when new building materials replace concrete, this word may come to only mean not abstract. 2. Tense. Verbs are sometimes gradually turned into markers of tense for the past and future. The English word gonna provides a nice example of a word in transition to a grammatical element. Consider the sentence, I'm gonna stay here and not move. Clearly, gonna is from the verb phrase going to, but I just used it to express my intention to stay. Gonna has not fully transitioned yet, but it appears to be doing what the word will did centuries ago. Will is derived from a verb meaning want, which is a very common source for the future tense, for example in Swahili. Similarly, past tenses often evolve by modifying and then gradually trimming down the verb for finish or done. In the unwritten Yasawan dialect of Fijian I've been studying, this can be seen in a not yet trimmed down version, where the literal translation of I have eaten is I am eating done. 3. Prepositions. Adverbs often get retasked to create prepositions, like after or behind. For example, the body part word for back or buttocks often gets first modified into an adverb like behind. The sad events lay behind them. Then the adverb evolves into a preposition, as in, I put my laptop behind the door. In English, curiously, the euphuistic use of behind, as in get off your behind, to mean buttocks, is turning this preposition into a body part noun, which is rare. 4. Number and plural pronouns. Pluralization is often achieved by adding all to nouns and pronouns, and then trimming it down. For example, in the dialect of English spoken in the southern United States, a second-person plural pronoun has emerged in the form of y'all. This new pronoun, which many languages have, but no other dialects of English, arose as you crashed into an all that was added to remove any ambiguity about whether you was plural. Incidentally, y'all is not ungrammatical. It's an example of how languages evolve. If it feels wrong to you, that's because it violates one of your internalized linguistic social norms. 5. Subordinating conjunctions. Tools for marking subordinate clauses are often built from those for marking relative clauses, which are often built from verbal pointers, demonstratives like this and that. Verbal pointers in phrases like that picture or this hat evolve to mark relative clauses, as in Zoe likes the picture that Jessica painted. These relative markers evolve into subordinating conjunctions, as in I hope that Zoe likes the picture that Jessica painted. Practically speaking, learners have to acquire the relevant social norms for how they can and cannot arrange words to communicate, but these rules are gradually altered as successful communicators who have made adjustments to increase efficiency or expressiveness are preferentially attended to and learned from. This can even be seen in relatively brief experiments in which people first had to learn an unfamiliar grammar and then had to use it to communicate. In one experiment, after only 3 days of interaction, the patterns of a just learned grammar shifted in ways that increased communicative efficiency. Amazingly, the observed grammatical modifications parallel the actual distributions of these grammatical elements in real languages. All of this suggests that grammatical tools and rules should evolve like other aspects of culture. At some point, there must have been communicative repertoires that lacked some of the shared norms that languages have for referring to the past or future, marking number, or for embedding clauses. If true, we might find existing or historically known languages with smaller toolkits of grammatical tools or less efficient grammatical rules, just as we do for technologies. However, it may be that such tools, once they emerge in one language, rapidly spread to other languages, as good counting systems do. This would prioritize looking at more isolated groups or languages that may not have had time to adopt the new tools, or by looking back in time at past languages using ancient written sources. Supporting this expectation, subordinating conjunctions like after, before, and because of may have evolved only recently, in historical times. and are probably no more a feature of human languages than composite bows are a feature of human technological repertoires. The tools of subordination seem less well developed in the earliest versions of Sumerian, Akkadian, Hittite, and Greek. This makes these languages slow, ponderous, and repetitious to read. Subordination tools also seem to be missing in some living languages, including languages found in Australia, for example, Warlpiri, the Arctic, Inuit, New Guinea, Yatmul, and the Amazon, Piraha. People use phrases that are subordinate to some degree, but this subordination is provided by a combination of concatenation and context, not by specialized grammatical tools like coordinating conjunctions. To see what I mean, here's subordination using only concatenation and context in action, in English. I'm taking Sharon's son to the circus next week. She's the young woman we met last week. We were outside the Starbucks. Philosophers have long been impressed by language's ability to embed phrases within larger hierarchical structures, often using grammatical tools for subordination. However, these findings suggest that much of the hierarchical structuring and fancy subordination that we see in most modern languages is the product of long-term cumulative cultural evolution. This is not to say that we humans don't have some souped-up innate abilities for dealing with hierarchical structures, which may also be useful for making tools or understanding social relationships, but merely that the elegant bits of grammar that permit us to fully harness these abilities were built by cultural evolution. Finally, grammatical complexity, like other aspects of culture, is influenced by social institutions and adapts to the demands of the communicative contexts of a society. For example, larger populations with more heterogeneous speech communities and more adult language learners tend to have morphologically simpler grammars. In morphologically complex grammars, words have many different, often subtle, grammatical elements that must be inserted, at the front or back or in the middle. These elements augment the meaning of the word, conveying tense, mood, number, gender, etc. Morphologically simpler languages do much less of this, but can, often, communicate the same information with additional words and word ordering. One interesting explanation for this is that larger populations have more adult language learners, and adult language learners are bad at learning morphologically complex languages. In summary, larger speech communities seem to possess bigger inventories of words, phonemes, and grammatical tools. That is, the languages possessed by these communities are more complex. Historical evidence suggests that inventories of words and grammatical tools have expanded over centuries and millennia. Psychological evidence indicates that the contents of vocabularies and the rules of grammar, such as those related to color terms and integers, may alter our cognitive abilities, including both memory and perception. A combination of evidence indicates that modern world languages may in fact be rather unusual compared to most of the languages spoken over our species' evolutionary history. Culturally evolved to be learnable. As our communicative repertoires gradually expanded, there would have been both selective pressure on our genes to make our ancestors better at learning culture, including the elements of these emerging communicative systems, and pressure on the repertoire of communicative elements to be more learnable, especially by children. Here, I'll briefly emphasize the role of the second partner in this duet, culture. Like other kinds of tools, which have evolved culturally to fit our hands, shoulders, and physical abilities, languages have culturally evolved to fit our brains, becoming more learnable by adapting themselves to the contours and constraints of our psychology. Remember the color terms. Children are good at learning languages, in large part, because difficult-to-learn elements don't get learned, and, ergo, don't get transmitted to the next generation. There are possible languages that are really hard for children to learn, but those lost out in competition to more learnable languages. Languages that more effectively exploit innate aspects of our psychology would be more learnable and less likely to be replaced by alternatives in the future. Computer simulations of the process of cultural transmission across generations among imperfect learners with limited memories favors the emergence of many of the key traits that distinguish languages from the communication systems of other species. As the size of vocabularies increased, the cultural evolutionary pressure on languages to become rule-bound and regular would rise. A learner might be able to acquire, for example, an idiosyncratic past tense form for each verb in a language with a small lexicon of, say, 50 words, but they won't be able to do it for a language with 5,000 words. Thus, languages without such rules, syntax, didn't make it. They got beaten out by those languages with more regular rules, like adding ed for the past tense, that children could learn to apply. This will be the case both because it's tough to remember all those specific cases, and because, as vocabulary size increases, many more specialized verbs will only be heard rarely. Irregular forms can persist, like ate instead of eated, but only on frequently used words, where the constant repetition eases such memory constraints. Direct evidence for these processes in human evolutionary history is non-existent. However, complementing the computer simulations mentioned earlier is indirect evidence from laboratory experiments, like those described for the accumulation of technical skills in Chapter 12. These experiments show that when people observe the performance of others using an artificial language and then make inferences from those observations, both structure, syntax-like forms, and compositionality, discrete words, emerge over many transmission events as people learn from each other over many laboratory generations. No single individual does much at all, and no one is trying to achieve this as a goal. It's an unconscious, emergent product of cultural transmission over generations. Research with children speaking real languages further confirms that regularity makes languages more learnable. Children speaking more regular languages understand sentences like, "The horse kicked the cow," better than children who speak less regular languages. Specifically, Turkish and English-speaking children outperform children speaking the quite irregular Serbo-Croatian language. Of course, these performance differences vanish in later years. Nevertheless, such research suggests that not all languages are equally easy for kids, or adults, to learn. My point is that cultural evolution is a key reason why existing languages are so easily learned by children, and some of the recurrent features of languages, like syntax, are likely the result of cultural evolution working to keep languages learnable, especially as vocabularies expand. The synergies of manual skills, norms, gestures, and speech. During our species' evolutionary history, coevolution was relevant in two important ways. First, increasingly complex communicative repertoires were co-evolving with increasingly complex tools, practices, and institutions. This coevolutionary interaction was synergistic, since two or more of these domains of culture will create selection pressures for genes that improve our psychological abilities to acquire, store, organize, and retransmit valuable cultural information. This interaction will sharpen our abilities to culturally learn from others, improving our skills at inferring others' goals and intentions, to better learn from them, inferring underlying rules or norms, and learning complex sequences with hierarchical structure. Second, as noted earlier, these culturally accumulating communicative repertoires put selective pressures on genes for communicating. They pushed down our larynx to widen our vocal range, drove axonal connections from our neocortex down deep into our spinal cords to improve the dexterity of our hands and tongues, whitened the sclera of our eyes to reveal our gaze direction to cue others, and endowed us with reliably developing cognitive skills for vocal mimicry and communicative cueing, like pointing and eye gaze. It's impossible to know in what behavioral domain cultural evolution first began to accumulate, in tool making, food processing, or gestural communication. It's also plausible that cumulative cultural evolution in some ancestral groups began with gestural repertoires, while other groups, due to different ecological constraints, started to accumulate techniques for tool manufacture. The key point is that whatever came first would have likely catalyzed developments in the other domains. For example, human brains have axons that project from our neocortex directly to the ventral horn, where the motor neurons are, and then down deep into our spinal cords. This anatomical change helps to explain our species' impressive manual dexterity, and specifically our ability to learn tasks requiring manual dexterity. This change would have been favored by the cultural emergence of techniques requiring greater dexterity, like making nets, clothing, blades, or fire, or culturally transmitted skills and tactics, like using projectiles such as rocks, clubs, or spears for hunting or defense. Plausibly, either an emerging gestural communication system or increasingly complex tool-making skills could have created genetic selection pressures favoring more direct axonal connections into the ventral horn and spinal cord. If gestural communication emerged first, it's plausible that tool-making skills would have benefited from enhanced dexterity. If it were tools driving the boat, then enhanced gestural communication would have gotten the free ride. Better communicative skills might also have improved the quality of the information transmitted about making and using tools. This process helps explain our species' impressive tongue dexterity and capacity for vocal mimicry, which are unique among primates. Vocal mimicry is rare in nature, although many bird species who are also excellent vocal mimics have an analogous brain setup. Our neocortical projections, which also innervate the muscles of our jaws, tongue, face, and vocal cords, could have initially been driven by gestural communication, tool making, or any number of other skills. However, once they spread, they could have opened the door to learning vocalizations as a byproduct. Vocalizations would have first developed as an addendum to an existing repertoire of communicative gestures, which could have included facial expressions, pointing, and bodily positions. In this scenario, the genetic selection pressures for speech would have been created by a non-speech-based communicative repertoire that gradually favored adding speech elements as a way of freeing the hands and suppressing the need to necessarily look at each other. The crosstalk between the tongue and limbs is highlighted at weddings, when inexperienced dancers stick their tongues out while focusing on challenging dance moves. Whatever the precise evolutionary sequence was for the emergence of gestures, vocalizations, social norms, and tool use, is not crucial, since cultural evolution would have created substantial genetic evolutionary pressures for using verbal gestures, speech, to communicate, to free our hands for using tools, throwing weapons, cooking, communicating at night, and maintaining balance while running down prey. Comparative work with other apes shows that our larynx dropped, which lengthened our vocal tracts and expanded our potential phonetic repertoire. Our tongues were freed up to move both side to side and up and down. We also lost the soft, inflatable air sacs that apes have around their larynx. These changes, however, came with a significant cost. Other mammals, and human infants, can breathe and swallow at the same time, and thus can't easily choke on food. Older humans can, and do, choke. These genetic evolutionary selection pressures were for communication in general, not only for spoken language, and our ancestors may have maintained gestural languages alongside spoken languages, as many modern hunter-gatherers did. In the increasingly cooperative worlds constructed by social norms and reputations, it became relatively more important to communicate and teach others, rather than deceive or exploit them. Such pressures explain why humans are peculiar in having our rather small irises set against a white background, the sclera, in our eyes. Anyone watching us can infer where we are looking or whom we are looking at. Experiments with apes and infants show that apes watch the orientation of the heads of others, while human infants watch the eyes. This behavior makes it harder for people to hide what they are interested in, a cost, but it is quite useful for actively transmitting cultural information or communicating more generally. Motivated to convey cultural information, diverse populations around the globe make use of a somewhat variable set of pedagogical cues to facilitate learning. Commonly used cues include eye contact, head movement, and pointing. With infants, people in diverse societies speak in motherese, baby talk. With its slow and exaggerated intonations, motherese speeds language learning by providing input that is easier for infants to process. Recognizing that languages, or at least simpler communicative systems, were co-evolving with tools, practices, and social norms helps explain how some of the features of languages might have evolved and why. For example, linguists are often impressed by the hierarchical structure, sequential ordering, and recursion found in modern languages. In a world with only language evolving, it's not obvious where the cognitive abilities that underlie these patterns might have come from. If a genetic mutant with new mental abilities for creating hierarchical linguistic structures emerged in a society having only a simple proto-language, she wouldn't have anyone with whom to use her advanced abilities. No one lacking her cognitive abilities could understand her or could copy her complex patterns. However, complex tools are also assembled sequentially, hierarchically, and sometimes recursively, just like most modern languages. To make a spear, you have to obtain the wood, straighten it, and balance it for throwing. Then, or maybe first, you have to obtain the flint, bone, or obsidian to make the spear tip. This material has to be knapped or carved to make a spear point. Then you need some sinew or resin to attach the spearhead to the shaft. Thus, there are componential parts, objects, actions, knapping, and rules and orders for assembling the parts. All of this has to be done with the goal of obtaining a good spear, just as sentences are assembled with the goal of communicating. Similarly, food processing techniques to detoxify seeds, such as nardoo or acorns, are similarly sequential protocols with components and subcomponents, grinding, leaching, and cooking, which must be done in order. Beyond sequences and hierarchies, some technical skills, like weaving and knitting, demand recursive applications of the same techniques in a manner that could potentially continue without bound. Here, however, unlike language, there is no need for someone else to have the same abilities to get the benefits. It's directly beneficial to the individual to be able to organize and make a more complex tool. And the existence of these more complex tools will put an even greater selective pressure on those who cannot make them. These cognitive abilities can get redeployed for organizing and transmitting communicative repertoires, or perhaps in transmitting norms and practices about kinship systems. Consistent with this, when humans compete with primates in sequential learning tasks involving manual actions, we achieve superiority only when the task involves a hierarchical structure. This idea has been explored in computer simulations in which neural networks had to retain a genetically evolved ability to learn complex sequences in a non-linguistic task, like Nardu processing, while at the same time facing the challenge of learning a grammar. The neural networks would evolve genetically to be better learners of the grammar, and the grammars could evolve culturally to be more easily learned by these networks. The results are threefold. 1. Genetically evolving to learn non-linguistic sequences improved grammar learning. So, synergy does exist between tools and languages. 2. But having to remain a good non-linguistic sequence learner, a tool maker, inhibited genetic evolution's ability to improve grammar learning. So, no genes specifically for grammar learning are favored. 3. Nevertheless, neural networks got much better at learning grammars because the grammars evolved culturally to be readily learnable by the existing neural networks. In short, cultural evolution made the grammars more learnable. Genes and brains for learning complex sequences. Researchers may have isolated a gene that was favored during human evolution to improve our procedural or sequence learning abilities. The gene, FOXP2, which is located on human chromosome 7, codes for a protein that influences brain development, particularly in regions related to procedural and motor learning. For 170 million years, this gene appears to have remained relatively fixed across many species. However, since we split with chimpanzees only 5 to 10 million years ago, there have been 2 changes in our copy of the gene. Mutations in FOXP2 influence both grammar and sequence learning in humans and motor skill learning in mice. The indirect pathways that connect genes to mental abilities usually make firm links difficult, but it's plausible that FOXP2 was favored by cumulative cultural evolution to improve our procedural, motor, or sequential learning abilities for learning complex, culturally emerging protocols for tool making. Once in place, these abilities could have been harnessed in our communicative repertoire to permit more complex grammatical constructions. Or perhaps the sequence was the other way around. Consistent with this, research applying brain imaging techniques shows that using both language and tools, manual actions, involve overlapping brain regions. In fact, if you focus only on regions that are specific to either tool use or to language use, you are left with few differences. The differences that do emerge seem trivial, such as language activating the auditory regions and tool use tapping motor regions. Brain regions once thought to be specific to grammar now appear to be used for tasks requiring sequential or hierarchical structuring and are tapped for complex manual procedures. Similarly, learning to make both sounds and tools tap the same imitative areas, so vocal imitation is not something totally distinct from other kinds of imitation in the brain. Even now, culture continues to be the primary driver of human genetic evolution, and the cultural evolution of different linguistic features in different populations may be continuing to alter gene frequencies. One suggestive bit of evidence indicates that the emergence of non-tonal languages may have created conditions favoring the spread of two different genetic variants. Many languages overlay pitch or pitch change on top of a set of sounds to distinguish different words. These are tonal languages. In Mandarin Chinese, for example, the sound ma can mean mom, horse, hemp, or scold, depending on the intonations or tonal contours. Non-tonal languages, such as English or Spanish, or any European language, only use pitch or intonation at the level of the phrase to convey emphasis, feeling, or mood. The two genes are variants of ASPM and MCPH, and influence brain growth and development, and these have begun spreading under natural selection in the last 50,000 years or so. Both new variants of these genes are associated with non-tonal languages. That is, speakers of non-tonal languages tend to have the new variants. Of course, the history of the spread of human populations means that many elements of genes and languages will be correlated, because they so often move together. Consequently, gene-language correlations are rampant and don't generally point to the action of natural selection. But in this case, it appears that historical relationships, linguistic similarities, and spatial proximity cannot explain the gene-language correlation. And so far, these variants cannot be traced to any other psychological or cognitive differences, such as intelligence, brain size, social skills, or schizophrenia. Nevertheless, to be clear, any human child raised anywhere can learn the local language, but natural selection may be tinkering with the genetics of just how easy or hard it is, which depends on the enduring features of local languages. Culture, cooperation, and why actions speak louder than words. The broad view I've presented in this chapter challenges many claims, old and new, that the emergence of language in our species' evolutionary lineage was the Rubicon that, once crossed, set us apart from the rest of nature. With the emergence of language, so the story goes, cultural transmission became possible, and the problem of cooperation was solved, basically by reputational gossip. While there is no doubt that language plays an immensely important role for our species, there are three main problems with this common view and its overemphasis on language. First, this approach fails to recognize that quite a bit of cultural transmission and cultural evolution is possible without language. Cultural information about tool manufacture, fire making, dangerous animals, edible plants, cooking, and diet, food choice, can all be acquired, at least to some non-trivial degree, without language. Even social norms, such as those related to food sharing, can be transmitted without language. A little way down the culture gene coevolutionary road, but long before full-blown language, more controlled pointing, facial expressions, and improvised pantomime could have provided communicative tools for cultural transmission, as these still do when people don't share a common tongue. Anything we might call language probably arrived on the scene well after cultural evolution was underway and had already assembled simple communicative repertoires. Second, language itself is a culturally evolved product, so it can't cause culture. Of course, language can and does greatly facilitate cultural transmission, the flow of cultural information, and opens up whole new pathways, such as the transmission of stories, labeled categories, and songs. But these new pathways were bootstrapped by non-linguistic forms of cultural evolution, just as the much later spread of writing and literacy was bootstrapped from language to open up new cultural evolutionary avenues. Finally, language has at its core a rather serious cooperative dilemma: lying, deception, and exaggeration. Lying with language is cheap, at least in the short term, and is a potentially powerful way to exploit and manipulate others. The more complex a communicative system is, the easier it is to lie or shade the truth, and get away with it. If this cooperative dilemma is not addressed, the evolution of language, whether by genetic or cultural evolution, is rather limited. The reason is straightforward. If others are using language to trick or deceive me, I can avoid this by not believing anyone, or even by not listening to them at all. If, to avoid being manipulated, everyone stops listening, then there's no reason to try to communicate. Language will go away or remain limited to those situations where deception or manipulation are too difficult. Thus, for complex communicative repertoires to evolve in the first place, this cooperative dilemma has to have already been at least partially solved. Therefore, language can't be the big solution to human cooperation. Of course, once culturally evolved social norms for honest communication emerge and spread, then language can potentially expand the sphere of cooperation and exchange by helping spread gossip about norm violators and by making the acquisition of social norms faster and more accurate. Many arguments regarding how language solves human cooperation assume, without acknowledging it, that culture already exists, because they assume reputations exist, and that these provide a policing mechanism for honesty. This presupposes both reputations and social norms about honesty, which are both culturally transmitted and highly variable across societies. In addition to social norms against lying, the cooperative dilemma of language is further mitigated by our cultural learning abilities in two ways. First, transmitting reputational information does not require language and can effectively be done with nothing more than pointing and facial expressions. For example, I can point at Bill lounging under a shady tree while we are rebuilding his house and make a disgust face or shame display. This will transmit to you my views of Bill's actions. So, the transmission of reputation isn't reliant solely on language. Second, although reputations are subject to manipulation, cultural learners already have cognitive abilities that would have mitigated the impacts of deception by self-interested others. For example, Steve might try to convince you that his rival, John, is a scoundrel so that Steve can gain an advantage on John. Suppose John is honorable. However, if you use conformist transmission in acquiring your beliefs about John, you would take input from many people in the community, most of whom would not be John's rival. This would allow you to discard Steve's disinformation and converge on a more accurate version of John's reputation. Thus, our cultural learning mechanisms help prevent lying and deception from destroying the value of reputations. Nevertheless, the emergence of language would still have created opportunities for individuals, especially those who are successful and prestigious, to manipulate others into doing or believing things that would benefit the manipulator. For example, a manipulator who wants to poison his competitors might try, using language, to spread the idea that blue mushrooms are delicious and nutritious, even though he believes they are mildly toxic. The potential for such manipulative cultural transmission would have created a selection pressure for learners to look for what I call credibility-enhancing displays, CREDs. CREDs are actions that a person would be unlikely to perform if he or she believes something different from their verbally stated beliefs, or if they prefer something different from their stated preferences. Using CREDs provides learners with a kind of partial immune system or filter against manipulators who would exploit the cheap cultural transmission channel provided by language. A good cred for actually believing that blue mushrooms are delicious and nutritious is to eat a lot of blue mushrooms and feed them to one's children. If a learner observes a potential model doing this, he should then be willing to weight the model's statements about the nutritional value of blue mushrooms more heavily, informing his own beliefs. Although research is just beginning, experimental work with children and adults suggests that creds are important for the cultural transmission of many beliefs and practices, including food preferences, altruistic behaviors, and supernatural or counterintuitive beliefs. Creds, for example, help explain why martyrdom can be a powerful force in spreading religious faiths. Anyone willing to die for their supernatural beliefs probably actually holds those beliefs and is not, or was not, engaged in some trickery or manipulation. Creds also help explain why religious leaders take vows of poverty and celibacy, because these creds make them more potent transmitters of the faith. Overall, creds provide a partial immunity to the opportunities for exploitation opened up by language, though, of course, the prevalence of con artists, phony TV evangelists, and other hucksters attests to the persistence problem created by our reliance on cultural learning through language. Our use of creds is why actions speak louder than words, and contributes to suppressing self-interested attempts to manipulate or exploit cultural transmission. Summary. Let me close this chapter with 7 take-home points. 1. Languages are packages of cultural adaptations for communication. Just as with technologies and social norms, once cultural evolution is unleashed, it will begin generating increasingly complex communicative repertoires adapted to local contexts. We've discussed that cultural evolution can even assemble sign and whistle languages, or alter the sonority of words to fit the recurrent acoustic environments faced by different speech communities. 2. These repertoires will evolve culturally to be learnable, and this learnability will create shared features among languages as they exploit diverse, non-linguistic aspects of our innate psychology. However, the details of this process will depend on who has to learn the languages: only children or people of all ages. 3. Like toolkits, the size and interconnectedness of populations favors culturally evolving and sustaining larger vocabularies, more phonemes, shorter words, and certain kinds of more complex grammatical tools, like subordinating conjunctions. 4. These patterns, combined with anthropological and historical evidence from diverse languages, suggest that widely spoken modern languages, like English, probably look quite different from the languages that dominated our species' evolutionary history, just as our technologies and institutions look rather different from those of small-scale societies. 5. Acquiring languages alters aspects of our psychology and endows individuals with new cognitive abilities. 6. As a recurrent product of cultural evolution, languages have produced powerful genetic selection pressures over the course of human evolution, shaping our bodies and brains for speech and cooperative communication. This process continues. 7. Understanding the evolution of language requires seating it within the broader context of the culture-gene coevolution of tools, skills, and social norms. In Chapter 14, we'll see some of the myriad ways in which culture shapes our brains and biology, even when it doesn't mess with our genes. Cultural evolution is a type of biological evolution.